the 2-point loads 𝐄𝐋 and 𝐄𝐋𝐄𝐓. What should be the distance r so that the force of Coulomb is F0? From the definition of Coulomb's law, we write the equation that relates 2-point electric charges, where Fij is the Coulomb force that particle J exerts on particle I. 𝐄𝐋 and 𝐄𝐗 are labels for the value of the load of both I and J, while K0 is the electrostatic constant equal to 1/4 pi epsilon 0, where epsilon is the constant of vacuum permittivity. The vectors ρ and 𝐴 are the vectors that go from the origin to the location of the particles 𝐄𝐋 and 𝐄𝐗. We are free to choose the reference system, so let's make the most convenient choice. Fix one of the particles at the origin. We put 𝐄𝐋 in the origin, so ρ is 0 and 𝐴 is equal to r. Thus, in the numerator we have the vectorless r. Meanwhile, in the denominator we take the module of less r, which is r, and then raise it at the third power. But the vector r has length r and points in the direction between the two charges, in this case in the x direction. Then we can divide the length r in the numerator by the module to the cube of r in the denominator. Thus, the force will be inversely proportional to the square of the distance and points in the negative direction of the x-axis. From the third law of Newton, the force F21, that is of charge 2 due to charge 1, will have same module, direction, but opposite direction. That is, it will point at the positive axis of the x-axis. Notice that in this convention you do not need to worry about the concept of attraction or repulsion between charges of same or different polarity. That is, this question is already within this convention. Because of 𝐄𝐋 times 𝐄𝐋𝐄 is positive, i.e. same polarity, the force between the charges will be repulsion. However, if the product between the two charges is negative, that is, with opposite polarity, the force between the loads will be attractive by reversing the force F12 and F21. To find out what the distance r must be for the force F to have modulus equal to F0, we take the module on both sides of the equation. Notice the absence of vector notation because now we are working only with numbers. We must isolate r square. Thus, we multiply by r squared on both sides and take the scalar product with the versor x hat and divided by F0 on both sides. As we want r and not r square, we extract the square root and select only the positive value, since there is no physical sense for a length of negative r. This is a physical step, that is, a choice of physics. Now we can replace the values. For example, in Halliday, Volume 3, 5th edition, Chapter 25, Exercise 2, we have 𝐄𝐋 equals 26.3 microcoulomb, 𝐄𝐋𝐄 equals minus 47.1 microcoulomb, and F0 equals 5.66 newtons. We take the load modulus, since we are using as criterion the force modulus F0. Thus, r should be equal to this value. Very easy, isn't it? If it hasn't been clear yet, try to follow the reasoning once again by going back to the video. This problem is also contained in the 12th edition of Halliday in Chapter 21, Exercise 3, slightly changing the values, but the problem is the same. The key to solving these problems is to abstract the value of variables and replace only at the end. In the next video, we will add a third charge.